So in the last session, we were discussing how the electrons are arranged in orbitals, and this table is important. The pattern, like first electron will go to 1s, then 2s, 2p, then 3s, 3p, 3d, 4s, 4p, 4d, 5s, 5p. So how the filling up, first electron will go to 1s, then it will be 2s, then from 2p to 3s, then from 3p to 4s. So why electron is not going from 3p to 3d instead of going to 4s? So whenever electron occupy, it will always occupy the orbital with low energy. So when we compare the energy of 4s and 3d, because 4s is having a low energy, even though it is higher from the shell, from the nucleus, it is higher because it is a fourth shell, and 3D is closer. But in terms of energy, 4s is having low energy and 3D is having high energy. So electron always occupy the energy level with low energy first. That's why first it will go to 4s. Once the 4s is complete, then it will complete 3D. So example, if you want to write the electronic configuration or electronic structure for, say, iron Fe, which is 56 and 26. So there are 26 protons and 26 electrons will be there because it's a neutral atom. So we have to arrange 26 electron, and we have to recall the idea: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. So we increase one orbital, and then we decrease, then 5s, 5p, 5d, 6s, 6p, and then 7s. So how the filling up will take place? So first electron will go to 1s, then 2s, then 2p, 3s, then 3p, 4s, then 3d, 4p, 5s, then 4d, 5p, 6s, and then 4f, 5d, 6p, and 7s. So if you want to arrange 26 electron, first it will be 1s. How many electrons will be there? 2. Then it will be 2s. How many maximum? Because s can maximum have 2, p maximum 6, d maximum 10, and f maximum 14. Then it will be 2p, 6, then 3s2. So right now we arrange 12 electron. Then 3p6, so we arrange 18 electron. Then from 3p it will not go to 3d, it will go to 4s. So it will be 4s2. So we arrange 20 electrons. We are left with 6. Then will be 3d, but the d maximum can have 10, but we are left with only 6, so we will write as 6. So this is the arrangement in terms of energy, because electron always occupy the orbital with low energy first. So this is in terms of energy. But in terms of order of the shell, because first we have first shell, then second, so we will have 1s2, 2s, 2p, 6, 3s2. We rearrange this, 3p6. Then because in terms of order, 3d will be first and 4s will be afterwards. And that's why these elements, you can see, they have incomplete inner shell is incomplete, outer shell is complete. The inner shell is incomplete and outer shell is complete. What we call these type of elements, we call them as transition elements. So for transition element, always the inner will be incomplete where outer will be complete. Is it clear? electronic configuration for chromium. Okay. So example, if you want to write the electronic configuration for chromium, so we have atomic number of the chromium is 24. So we have 24 electrons, we have to arrange 24 electron, and we have this table 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 6s, 6p, and then 7s. So we increase one orbital and then we decrease. Now arrangement of the electrons, 24 electrons, so it will be 1s2, 2s2, 2p6. So we arrange 10. Then it will be 3s2, 3p6, 4s2, so we arrange 20. And then it will be 3d4. Now when we write 3d4, there is one thing what happened, because when we have half filled orbitals and completely filled orbitals, they are more stable. So if you have half filled orbital or complete filled orbital, they are more stable. So what happened? Because S maximum can have two. So what will be half of S2? It will be S1. And same thing, D maximum can have 10. So what will be half? It will be 5. So what happened in case of chromium? Because right now S is complete, but 3D is incomplete, partially completed, not half. So one of the electron jumps from S to D to make it more stable, because I told when orbitals are either half stable or completely filled, they are more stable. So here S is stable and D is unstable. So how to make it stable, more stable? One of the electron from S jump to D. So when one of the electron jumps from S to D, now what become 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. So this is half filled, so this is stable, and this is also half filled, that is also stable. So both become stable when one of the electron jumps. That's why this is the exception what happened in chromium. Is it clear? So this is basically an exception. This is not happening for all of them. For few of the elements, just to make them more stable, electron jumps from S to D to make it half filled, which make them more stable. Then the shapes of these orbital, as we already discussed, the previous electron in a box model. So S is having only one box, P is having three boxes, D will have five, and F will have seven boxes. So example, we arrange oxygen, which is 8 and 16. So 8 electrons are there, 1s2, 2s2, 2p4. Electron in a box model, because this is in terms of energy. When we say electron in a box model, so first we'll have 1s, then we'll have 2s, and then we'll have 2p. You can make separate boxes for 2p, like three separate boxes, or you can make the boxes joined together. So 1s2, so 2 electrons, 2s2, then 2p4. So 1, 2, 3, and then 4. This is how the electrons are arranged in an atom of oxygen. 1s, 2s, and that is 2p. Is it clear? Then the shapes of these orbitals, the s orbitals are spherical, where p orbitals are dumbbell. And p is actually divided into three axes, three dimensions. So we have x-axis and we have y-axis and z-axis. So three dimensions. So what is the shape of the p? It is dumbbell. So this will be there px, which is in the x-axis. Then it will be py, which is on the y-axis, and pz is on the z-axis. And each of them can have two electrons. That's why the total p, so actually p is a combination of what? It's a combination of px, like p orbital in x-axis, p orbital in y-axis, and p orbital in z-axis. And each can have maximum two electrons. That's why the total electrons in p orbital can be 6. And this region, this is the shaded region, also known as the electron density. What does it mean? It means probability of finding electron is maximum. Like we can find electron within this region, anywhere within this region. So we call that as an electron density map. So Px, Py, and Pz are actually the parts from P subshell or P sublevel. So P sublevel is divided into orbital, the px, py, and pz. And actually our periodic table is also divided into blocks. The first two groups, group 1 and 2, are known as S block element, because group 1 and 2 are known as S block element. Helium even it's there in group 8, but actually in terms of blocks it is in group S block element. Then from group 3, 4, 5, 6, 7, and 8, these are known as p block element. Why we call them as p block element? Because the last electron is there in the p subshell. And then we have d block element. Between s and p, the element are known as d block element, because they have their last electron is in the d. And lanthanide and actinide series, that is known as the f block element, because their last electron is there in the f block or f orbital. Is it clear the distribution of the electrons in terms of blocks? So S, P, D, and F, these are the 5 blocks, and the 4 blocks. By mistake, I said 5. It's 4 blocks, and electrons are arranged in these 4 blocks. And according to the periodic table, we can locate their position. Now, what is the meaning of ionization energy, or the first ionization energy? Energy required to remove the electron from neutral gaseous atom. So how much energy we need to remove the electron from a neutral gaseous atom, we call that as ionization. If we are removing the first electron, like we have hydrogen, hydrogen is a molecule. If we remove electron from the molecule, we don't say it's an ionization. First, what we should have atom. So we should have atom in a gaseous state. We supply energy so that electron is being removed and it will form a positive ion. So the energy which we supply so that the electron is removed from the shell, we call that as first ionization or ionization energy. Same way, if I say we have sodium atom but in a solid state, and we supply energy turned into sodium atom, sodium ion in a solid state. Is this an ionization energy? Yes or no? We supply energy to sodium in a solid state. Is the energy supplied is known as ionization energy? So that is not an ionization energy. Why it is not an ionization energy? Because this sodium is there in a solid state. But according to ionization or definition of ionization, the energy required to remove electron from gaseous state of atom. Like we should have atom and we should have a gaseous state and we supply energy, so we call that as ionization energy. Same way, if we have oxygen molecule in a gaseous state, we supply energy and we remove electron. Can we say this as an ionization? No. Why we cannot say no? Why we don't say yes basically? So why we don't say yes? Because it's a molecule of oxygen. It is not an atom. So for ionization, number one, it should be an atom, and number two, it should be in the gaseous state. So when atom in the gaseous state and we supply energy to remove electron, we call that as ionization energy. If we remove the first electron, a plus one charge is there, we call that as the first. And if we remove the second electron, we call that as second ionization energy, or the second electron is basically removed, so the charge will be plus 2. Is it clear? The concept of ionization energy? So when we sketch a graph for log of ionization energy and the number of electrons removed, why we are taking a log of ionization energy? Because logarithm reduces the value, like because these are big values, but when you take a log it reduces the value, so you can plot them on the same scale. And on x-axis we have number of electrons removed. Example, we have sodium. So first we write the electronic configuration of sodium. 11 electrons are there, so it will be 1s2, 2s2, 2p6, and 3s1. This is the electronic configuration. So where the electron is removed first, whenever we remove the electron is always removed from the last shell. So number of electron removed: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So because we have to remove 11 electron. So when we remove the first electron, from where the first electron is removed, from 1s or 3s? The first electron, when we supply energy to sodium in a gaseous state to remove electron from sodium ion, from where this electron is being removed? Which shell? 1s or 3s? So when we supply the energy, the electron is always removed from the last shell, because this is the last shell and this is the first shell. First shell is closer to the nucleus, last shell is away from the nucleus, so which is loosely bounded. So electron is always removed from the last shell. So first electron is removed from the last shell, and we need less energy. These can be any numbers. Here the energy is increasing. So to remove the first electron, we need less energy. So this electron is removed from 3s. Then the electron is removed from 2p. And you can see, like in terms of shell, what you have, you will have the first shell. You will have the first shell, then the second shell, and then the third shell. Third shell is far away from the nucleus. Second shell is closer to the nucleus, and the first shell is too close. So to remove electron from the last shell, we need relatively smaller amount of energy. But when the electron is removed from second shell, so it is closer to the nucleus, we need a greater amount of energy, so there will be a big jump. So second electron third electron, fourth electron, fifth electron, sixth electron, and 7, because one is already removed. So these all electrons, from which shell they are removed? They are removed from 2p. This was removed from 3s. So they will have a comparable energies because they're in the second shell, all these electrons, same subshell as well. So they will have comparable energy. Then when we remove the electron from 2s, there will be a jump, but not too big jump. A small jump will be there, that when we remove the 8th electron and the 9th electron, there will be a small jump. That is because the electron is removed from 2s. But why there was a big jump? Because the shell changes. So whenever the shell changes, the ionization energy will have a bigger jump, because the second shell is much closer as compared to third shell. And when orbital change, there will be a jump, but it will be a smaller jump, because orbitals, it is belong to the same shell, but it is having a different subshell. And when we remove the electron from 1s, again there will be a big jump. So why there will be a big jump to remove the 10th and the 11th electron? Because they are very close to the nucleus. So there will be a very big jump. Is it clear? Why this is a jump? Because the shell changes. Why this small jump is there? Because the subshell changes. And again, why there is a big jump? Because the shell changes. Is it clear? This graph for log of ionization energy and the number of the electron removed from the atom. Same way, we can have aluminium, which is 13 and 27. So when we write the electronic configuration, 1s2, 2s2, 2p6, 3s2, 3p1. So we have log of ionization energy and the number, because there are 13 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13. So there are 13 electrons. Now, uh, so first we remove the electron. So first, from where the electron is removed? From 3p. The first electron is removed from 3p. So example, this is for 3p. Then the second electron is removed from 3s. So between 3p, because the orbital change, so there will be a jump, but it will be a smaller jump. Then another electron is also removed from 3p. So say when it is the same, so they will have a comparable energy. There will be a gap difference, but small difference, very small. Then another electron removed from 2p. So when electron is removed from 2p, so there will be a very big jump. So 2p, then another electron from 2p, 2p. So until all 6 electrons are removed from 2p. So 1, 2, 3, 4, 5, and 6 electron removed from 2p. And then after 2p, the electron will remove from 2s. So the 2s means there's the same shell, but subshell is different. So there will be a gap, but a small difference. So this will be 2s. And then from 1s, both electron. So there will be again a big jump for 1s. So this is for 3p. This is for 3s. This is for electrons of 2p, electrons of 2s, and then electron of 1s. Is it clear? This graph for aluminium, the ionization log of ionization energy and the number of electrons removed from aluminium atom. Then using the numbers, we can also identify how many electrons are there in the last shell. So example, if I say the successive ionization energy, of element are given. 400 is there, then 900, then 1900, and then suddenly 7000, then 9200, 9000 is there, and then 11200, and so on. So if the question is identify which group this element belongs to, so how to identify? Look here, if it is 400, it become double. 900, 900 double is 1800, but it is approximately 19. But when you check the difference between the third and the fourth ionization energy, so this is not following a sequence, there is a big jump. So when there is a big jump in the values of ionization energies, so it means the shell changes. So these are the electrons which were there in the last shell, because electrons are always removed from the last shell. So these are the electrons which are present in the last shell. So using the number of electron in the last shell, we can identify that this element belongs to group 3, because 3 of the energies are successive energies, ionization energies are comparable, like only multiplied by 2, but there is a big jump which shows that the shell changes. So we can identify that there are only 3 electrons in the last shell, and if 3 electron in the last shell, we can say that this element belongs to group 3. Is it clear, this example? Now, the factors which can affect the ionization energy, so 3 main factors are there which can affect the ionization energy. Attraction of the nucleus. So if there's a greater attraction, like more protons are there, it will have a higher ionization energy. Distance between the electron and the nucleus. If electrons are closer to the nucleus, it will have a higher ionization. And the shielding effect. What is the meaning of shielding effect? Like you have two different atoms, electrons are there, first shell 2, second shell 8, and third shell it is having 1, and another one, first shell 2, second shell only 1 electron. So when we compare for which one there is a greater shielding effect, so you can clearly see only for this electron, only 2 electrons are in the inner shell, so it will experience more force from the nucleus. But for the other one, there are many electrons within the near the nucleus, around the nucleus. So this electron will not experience the greater force from the nucleus. So this will have a greater shielding effect, and this will have a small shielding effect. And greater the shielding effect, the ionization energy will be less, because by supplying a small amount of energy we can remove the electron out. Here we need more energy to remove the electron out. So this will have a low ionization energy, this will have a high ionization energies. Is it clear? The concept of a shielding effect, that because basically what happened when electrons are there in the inner shell, like charges repel each other. So these electrons which are there in the inner shell, they are repelling the electron in the outer shell. So when they're repelling, this electron can come out easily, but here only 2 electrons are there, so less repulsion. So this electron, we need more energy to remove this electron out from the nucleus. So 3 factors which affect ionization energy is the distance from a nucleus, the charge of the nucleus, and the shielding effect. So this is a graph for ionization energy for carbon. So and it is a log of ionization energy because there's a greater difference, so normally we sketch for log. So when we write the electronic configuration for carbon, it is 6 and 12, so it will be 1s2, 2s2, 2p2. So when we remove the first electron, it will remove from 2p, the second electron also from 2p, the third electron from 2s, then another from 2s, and then from 1s, and then from another 1s. So when we remove this electron is removed from 2p. This is also from 2p, then 2s, then 2s, and then you can see a big jump. So that is 1s and then 1s. And how to identify from these values? As you can see, 590 approximately double is there, which is like 600, double is 1200. Then it is 5000, sorry, 4960, 940, then 6000, and then, so how to identify the number of electron in the last shell? So these are comparable energies, like this is 5000, so only 1500 difference is there between them. But then there's a big difference between the fourth and the fifth. So when you are checking this, 5,590 and then 1,150. So, and when you check this, the third one, so what you find? You find a big jump. So when you find a big jump, what you can identify because of this big jump, you can identify that the shell changes. So if the shell changes, how many electrons will be there in the last shell? So it will have 2 electrons in the last shell. So if it is having 2 electrons in the last shell, it means it belongs to group 2. Is it clear, this example? Now when we sketch a graph for ionization energy of the elements in the group and in the period, in the same, belongs to same period. Now what happened? We see a pattern. So normally what happened when we move across the period, so across the period the size of the atom will decrease and the charge of the nucleus will increase. So if the size is decreasing and the charge is increasing, so what should happen to ionization energy moving across the period? So ionization energy should increase. But practically what happened? What we find not all the elements are following the same trend. So if we sketch for elements in the same period, like example, we have lithium, then we have beryllium, then we have boron, then we have carbon, nitrogen, oxygen, fluorine, and then neon. Lithium is 3 atomic number. We need atomic number only. So lithium is 3, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, and neon 10. So if I sketch a graph for ionization, as we know, moving across the period, the size is decreasing because there is a greater nuclear charge. So, electrons are closer. So what it should happen when we sketch a graph for ionization energy or log of ionization energy and the element atomic number like lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So what should happen? The ionization energy should increase. So we should have a graph, a straight line. Values should be there, where it should be increasing. But in practical, that's not true. So in practically, all the element does not follow the trend. Some element shows that they have a different trend. So for this, we should first write the electronic configuration for each element. So example, for second period, because in the first period we have only two elements, hydrogen and helium. For a second period, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So when I write the electronic configuration, lithium 1s2, 2s1, 1s2, 2s2, 1s2, 2s2, 2p1, 1s2, 2s2, 2p2, 1s2, 2s2, 2p3, 1s2, 2s2, 2p4, 1s2, 2s2, 2p5, and 1s2, 2s2, 2p6. So when we sketch a graph for these elements and their ionization energies, or log of ionization energy, so we have lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. First, because lithium, and in terms of size, when we compare the size across the period decreases. So ionization energy, and they all belongs to the same shell, but the size is decreasing, the size of the atom. When we remove the electron from lithium, we remove from 2s. So example, this is a value for lithium. Then when we remove the electron from beryllium, because it's a complete shell and it is difficult to remove electron from complete shell, so beryllium will be higher. Size is smaller and the shell is complete. But when we check for boron, it should be higher, but it is not higher than beryllium, it is less than beryllium. So why a boron is having a lower ionization energy, the first ionization, than beryllium? That is due to a shielding effect. Because when we talk about beryllium, for beryllium we are removing electron from 2s, but for boron we are removing electron from 2p. So when we remove electron from 2p, how many inner shell electrons are there for beryllium? For boron, how many inner shell electrons are there? 4. For beryllium, we are removing electron from 2s. So when we are removing electron from 2s, how many inner shell electrons are there? Only 2 electrons. So which will have a greater shielding effect? So boron will have a greater shielding effect. And when the atom is having a greater shielding effect, its ionization energy will be low. So this will have a low ionization energy, and this will have a small shielding effect. That's why its ionization energy will be high. Is it clear? Why boron is having a lower ionization energy than beryllium? But it will not be too low, it will be between beryllium and lithium. Then moving on, because shells, the size is decreasing, so carbon size is much smaller. That's why it will have a higher ionization energy. Then nitrogen will be higher. But when we move from nitrogen to oxygen, again we find that oxygen is having a lower ionization. So first there was for group 2 and 3 due to a shielding effect. But why nitrogen, which is belongs to group 5, and oxygen belongs to group 6, why oxygen is having a lower ionization energy than nitrogen? So the reason is when we write the electronic configuration for nitrogen, it is 1s2, because nitrogen is 7 to, or 2s2, 2p3. So electron in a box model, so there will be a pair of electrons here, and first they will occupy singly. When we write for oxygen, in case of oxygen, so first shell 2 electron, the electronic configuration, if I write, it is 1s2, 2s2, and 2p4. So clockwise, anti-clockwise, and the first they will occupy singly, and then there is a pair. So you can see in the orbital there is a pair of electron. So there is a pair of electron, they will have more repulsion. But in case of nitrogen, all are single. So they will have less repulsion. So if there is a pair of electron, they have more repulsion. So it will be easy to remove electron. That's why when we check oxygen, oxygen will need less energy compared to that of nitrogen. So group 6 compared to group 5, they will have lower first ionization energy. And then we move on. Fluorine will have higher because the size is decreasing and the charge of the nucleus is increasing. That's why ionization energy will increase. And neon will be the highest one because a complete shell. So when we complete this, so there are two dips. One is between group 2 and 3. Another one is group 4 and 5. So between group 2 and 3, why there is a difference between 2 and 3? Because of shielding effect. And why there is a difference between 5 and 6, like 5 is higher and 6 is smaller? Because of the pair of electron present, they will have more repulsion. That's why it will be easy to remove electron as compared to that of group 5. Is it clear? The ionization energy graph for period 2. Any doubt? Same way, if it is period 3, as you can see, this is about the periodic table, first 20 elements. So you should practice for first 20 elements. First we have, like, this is period 1, then this is period 2, and then period 3. So hydrogen is there, then helium will be have the highest. Why helium is having the highest ionization energy? Because it's have only one shell that is complete and very close to the nucleus. That's why the highest ionization energy in terms of element is for helium. For period 2, lithium, then beryllium group 2, then boron group 3, you can find there's a difference. Then carbon group 4, nitrogen group 5, and oxygen group 6. Again, you find a difference due to the pair. Then fluorine group 7 and neon group 8. When we check third period, so sodium is group 1, magnesium group 2, and aluminum group 3. So why group 2 and group 3 have a difference? Because the subshell changes, the shielding effect is different. And then group 5 and 6 are different because there is a pair of electron. That's why it does not follow the same trend. Is it clear, this graph? So if they ask a question, these are the questions from the past paper. So if they ask the question, why helium? is having the largest first ionization. So what is the reason for that? Because helium electronic configuration is 1s2. So the first shell is there and only 2 electrons, and it is having 2 protons, and it is the smallest atom. So its first electron is in the first shell, which is closer to the nucleus. So it does not have any shielding effect because we are removing electron from this first shell. So there is no inner shell electron. So there is no shielding effect. As there is no shielding effect, that's why helium has a bigger first ionization energy compared to that of hydrogen. Is it clear? Even though hydrogen also does not have any shielding effect, but because hydrogen is having only one proton, where helium is having 2 protons, so 2 protons, we need more energy as compared to 1 proton. And why do the first ionization energy decrease down the group? So why the first ionization energy decreases down the group? Because when element belongs to the same group, they will have same number of electron in the last shell. So when we sketch the shell, like this is group 1, lithium is there, then sodium is there, and potassium is there. So when you check, even though the nuclear charge is increasing, but what happened, this will have more electrons, potassium, sodium will have less electron, lithium will have few electrons. So when we go down the group, what happened, the shielding effect increases, and the distance also increase. Distance between the nucleus and the electron, that is also increasing. So to remove electron from lithium, we need more energy, but to remove electron from potassium, we need less energy. So as we go down the group, the outer shell electron are far from the nucleus, and there's a more shielding effect. That's why the ionization energy decreases. Is it clear? So greater shielding effect, less attraction towards the nucleus, and if electrons are far away from the nucleus, they have less attraction. That's why the ionization energy decreases as we move down the group. Is it clear? The concept of ionization energy and the trend in the ionization energy. Then another similar question: why is the journal increase in first ionization across the period? Why generally the first ionization energy, when we move across the period, why it increases? Because what happened, the size is decreasing and the charge is increasing. So as we move across the period, the number of the proton increases, an electron is added in the same shell, so they will have the same shielding effect. That's why the ionization energy generally it increases, but there are few elements from group 2 and 3, like group 3 does not follow the trend and group 6 does not follow the trend. Why sodium has a much lower ionization energy than neon? So when we write the electronic configuration for sodium, it is 1s2, 2s2, 2p6 and 3s1. When we write for neon, it is 1s2, 2s2, 2p6. So for sodium, we have to remove electron from 3s. And for neon, we have to remove electron from 2p, which is closer. And second thing, sodium, there are more inner shell electron. For neon, less inner shell electron. So it will have a less shielding effect. That's why more ionization energy. Sodium will have higher shielding effect. So less ionization energy. Is it clear? Discussion. And same way, why there's a small drop from magnesium to aluminum. So why the ionization energy changes from magnesium to aluminum? Because when we write for magnesium, it is 1s2, 2s2, 2p6, 3s2. For aluminum, it is 1s2, 2s2, 2p6, 3s2 and 3p1, because aluminum will have more inertial electron, magnesium will have less, so this will have a greater shielding effect. That's why ionization energy will be less. And for phosphorus to sulfur, as this is the electronic configuration of phosphorus, singly they are occupying, but there's a pair of electron in sulfur. So due to this pair of electron, there's more repulsion, so it will be easy to remove electrons. So you have to learn carefully the explanation. For group 2 to 3, it will be same reason. So they can change the element, they can ask here beryllium and boron, and they can change the element, they can ask nitrogen and oxygen, but the reason will remain the same. In terms of orbital you will change, but the main reason will remain same. So this was about the ionization energy. Today's session we discuss the topic ionization energy, and you can see the periodic table is divided into S, P, D and F. And this is about the atomic radius. As we move across, the atomic radius decreases because the nuclear charges increase. And we already discussed the trend in the first ionization for group 2 and 3, as well as group 5 and 6. About the melting point we will discuss in the next session. So I'll end the session and share this with you.